morning friends, up to 10.4 numerical of exercise we discussed. Now today 10.5 numerical of exercise. Here in Young's double slit experiment, a monochromatic light of wavelength lambda is used. The intensity at a point where the path difference is lambda is given as capital K. Capital K. Now, what is the intensity of a light at a point where the path difference is lambda by 3? Now listen here, wavelength of light used. Wavelength of light used is lambda. Right? For path difference, first path difference is given is lambda. The intensity of light or the intensity of point is I is given as the capital K. Is capital K. We have to find out the intensity at a point where the path difference is lambda by 3. For path difference is equal to lambda by 3. What is the intensity at a point? That means we have to find out the ideas. What is the intensity? Clear the same? Okay. For that purpose, the intensity of a light at a point where the interference pattern is formed. Already we know that there is the I is equal to I0 cos square pi by 2. We derive this equation 4. At a point where the path difference between the two waves of the superpositioning wave is pi. But here, the path difference is not given in phase angle pi. Here we are using this equation cos square k r2 minus r1 by 2. This k is wave vector. That is the wave vector. Already we learned in standard 11 chapter waves. That is the 2 pi upon lambda. 2 pi upon lambda. r2 minus r1 is the physical path difference at a point from the two sources S1 and S2. Clear the same? So we are using this equation in terms of the path difference. Therefore, the intensity at a point is I is equal to I0 cos square k r2 minus r1 by 2. Here k is equal to wave vector is equal to 2 pi upon lambda. 2 pi upon lambda. And r2 minus r1 is equal to path difference. Now at a point where path difference is R2 minus R1 is equal to lambda is given. At this point, what is the intensity? Therefore, I is equal to I0 cos square. Now, instead of the wave vector, we substitute the value 2 pi upon lambda. Physical path difference R2 minus R1 is also lambda and this 2 of denominator. So into 1 by 2. So 2 cancel, lambda cancel. Therefore I0 cos square pi. We know that the cos pi is equal to minus 1. Now cos pi is equal to minus 1. Therefore I0 into minus 1 whole square is equal to I0 is equal to I. But that is given as the capital K. That is capital K is already given. That is the equation number 1. Now at a point where path difference is I2 minus I1 is equal to lambda by 3. Therefore, I dash is equal to I0. Now, K wave vector I2 minus I1 upon 2. I2 minus I1 upon 2. Substitute the value. I0 is equal to K, capital K. Now here K is equal to 2 pi upon lambda into I2 minus I1, lambda by 3, and this 2, 1 by 2. 2 cancel, lambda cancel, therefore K. Here equal to I0 cos square. Here K I2 minus I1 upon 2. We substitute the value I0 as K, capital K, cos square. Here K is equal to 2 pi upon lambda, path difference lambda by 3 into 1 by 2, into 1 by 2. Therefore 2 lambda cancel. Therefore K cos square pi by 3. Now we know that cos pi by 3, 1 by 2. Therefore K 1 by 2 square. Therefore intensity at that point is K by 4. K by. So as the path lambda at a point is going to decrease from lambda to lambda by 3, so here intensity is also decrease here at point where the path difference is lambda. At that point the intensity is K. Now the point at which the path difference is lambda by 3, here the intensity is K by 4. Now next numerical is example number 10.6. A beam of light consisting of the two wavelengths lambda 1 is equal to 650 nanometer and lambda 2 is equal to 520 nanometer is used in Young's double slit experiment. Right? For first, find the distance of the third bright fringes. N is equal to third bright from the central fringe for the central bright maximum. So what is the X3? So already this type of the numerical we calculate for nth order bright fringes. We know that X and small d upon capital D is equal to n lambda. Therefore, Xn is equal to n lambda d upon small d. Okay. Now, n is equal to 3. Therefore, X3 is equal to 3 lambda d upon d. Now listen, in this question the value of capital D and small d is not printed in question. So here we have to consider the d is 2 millimeter. D is equal to 2 millimeter. That means the 2 into 10 is 2 minus 2 centimeter. Meter we convert. Meter. 2 into 10 is 2 minus 3 meter. And capital D is given as 120 centimeter. Therefore, 120 into 10 is to minus 2 meter. So this two value is not given in the numerical, we have to accept it. That is not printed in textbook. To obtain the answer according to our textbook, we have to consider the D and capital D as this value. Substitute here 3. Lambda we have to use for 650. For lambda 1, 650 nanometer. So 650 into 10 is to minus 9. Capital D 120 into 10 is to minus 2 upon small d 2 into 10 is to minus 3. Thus we obtain the answer is 1.17 into 10 is to minus 3 meter. So at this distance, the third bad fringe is formed. Third bad fringe is formed. Now in second part B, at what least distance from the central maximum, the bad fringes of the both wavelength are coincide. Again, in this numerical, the second part, we have to calculate the minimum distance from the central bad fringes at which the bad fringes of the both wavelength are coincide. Okay. So up to this, discuss we in next board, part B. Okay. So this 10.6 is most important. Maybe asked in board exam. Here. Now in part B, at what least distance from the central bad fringes? Now, the bad fringes of the both wavelength are superposed. First we have to understand, there is on the screen, here, this type of the bad fringes are A. There is the screen. There is the central bad fringes corresponding to the n is equal to 0. Now, for wavelength lambda 1, the bad fringes are these three. So there is the first bad fringes, there is the second, there is the third, there is fourth, and this three. For the particular wavelength lambda 1, n1 is equal to 1, n is 2, n is equal to 3, n is equal to 4. So this type of the bad fringes are formed or the obtained on the screen when we are using the lambda 1. Now, when we are using the lambda 2, the bad fringes are formed like this way. There is the n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5. Suppose at this point, here the both bad fringes are formed. That is for lambda 2. Instead of the lambda 1 wavelength of light, we replace the light with the wavelength lambda 2. At that time, the bad fringes obtained on the screen like this manner. Like to this manner. Just make. Suppose that is the n is equal to 4. N is equal to 3. N is equal to 2, n is equal to 1. So at this point, the bad fringes of the both wavelength are coincide. Suppose the distance is x. Distance is x. Our aim is to find out this x distance. Right? For both wavelength, here the distance between the two slits does not change, and also the distance of the screen from the slit also remain constant. That means the D and capital D are constant. Small d is here. Small d is our I think what I have given 2 millimeter. Therefore, 2 into 10 is to minus 3 meter. And capital D is 120 centimeter. So 120 into 10 is to minus 2 meter. For that purpose, we write like that way. Suppose at x minimum distance from a central bright fringe, the bright fringes of both in one and in two order of wavelength lambda 1 and lambda 2 are coincide. Therefore, xd upon capital D is equal to n lambda is equal to constant. Therefore, n1 lambda 1 is equal to n2 lambda 2. And from this, we can add n1 upon n2 is equal to lambda 2 upon lambda 1. Lambda 2, there is a 520, and lambda 1, 650, that means the 4 by 5. Thus, for lambda 1 is equal to 650 nanometer, n1 is equal to 4 bright, and for lambda 2 is equal to 520 nanometer, and 2 is equal to 5 bright fringes are coincide at x distance. Therefore, xd upon capital B is equal to n1 lambda 1 or n2 lambda 2 or n2 lambda 2. Therefore, x is equal to n1 lambda 1 capital D upon small d or n2 lambda 2 d upon small d. Now we substitute here this equation. X is equal to n1 4, lambda 1 650 into 10 is to minus 9, this, and capital D is given 120 into 10 is to minus 2 upon, now small d, 2 into 10 is to minus 3. So it's equal to 1.56 into 10 is to minus 3 meter. So at this minimum distance, the both bright fringes, that means for wavelength lambda 1 650 nanometer, fourth bright fringes, and for lambda 2 520 nanometer, fifth bright fringes are coincide at this distance from the central bright fringe. Clear this? If you use this equation, so also you get the same answer. Now next is example 10.7 of exercise. Now, angular width of a bright fringe is obtained in a medium is theta is equal to 0.2 angstrom, where the screen is placed at 1 meter distance from the slit, and wavelength of a light used is 600 nanometer. 600 nanometer. Now, what is the angular width of a bright fringe? When this element of the experiment is immersed in a water, that is in a medium. Now in water, having effect index n is equal to 4 by 3, we have to find out the angular width of the same fringes. Now listen, what is the angular width? First thing, there is the distance between the back fringes are shown. The distance between the two back fringes is our beta, and beta is equal to lambda capital D upon small d. That is the center point of the two slits. There is the S1, there is the S2. Angular width is this distance theta, and that is beta, and that is the screen D, distance of the screen. There is the back fringes obtained on the screen. Now, the distance between the two consecutive back fringes is beta. The angle obtained by the center point of the slit at the back fringes is theta, and this distance is the separation of the screen from the slit. That is the D. Okay. Therefore, tan theta. Theta is very small, so beta upon D. Beta upon D. That is the angular width. Okay. Now, in this example, what is given? In Young's double slit experiment, here the angular width of a back fringes is theta is equal to 0.2 degrees of K. Here the screen is placed at 1 meter distance from the slit, and the wavelength of the light used is 600 nanometer. Find the angular width of a back fringe when this instrument with such arrangement is immersed in water. Therefore, the distance between two consecutive back fringes is beta is equal to lambda D upon D. Therefore, angular width of a fringe, and this distance is known as the linear width. So it's equal to linear width of a fringe upon the distance of the screen. So it's equal to beta upon D. Beta is equal to lambda D upon small d upon D. That means the lambda upon D. That is our angular width theta. Now in water, angular width of a fringe is theta dash. Theta dash is equal to lambda dash upon D is equal to lambda upon N upon D. Therefore, lambda upon ND is equal to, now, that is our theta. So, theta upon N, theta upon N. Therefore, theta dash is equal to, theta is 0.2 degree upon 4 by 3. So it's equal to 0.15 degree. 0.15 degree. Here, lambda dash is equal to lambda by N. Only in first numerical of exercise, we find out the wavelength. If the medium is seen, so wavelength is also seen. Okay, again. The distance between the two consecutive fringes, actually that is known as the linear width. Linear width of a fringes is beta is equal to lambda D upon D. Now angular width is equal to linear width of that fringes upon D, or in other words, here we take the tan theta. tan theta is equal to beta upon d. Now this figure is only for your understanding how we write this equation. Therefore, theta is equal to beta upon d. We know that the beta is equal to lambda d upon small d. D cancel. Therefore, lambda upon d. So here theta is given, that is the 0.2 degree. Now this element is immersed in water. So what is the width of the black fringes? So the new angular width is equal to wavelength lambda dash upon d. Lambda dash is equal to lambda upon n by d. But the lambda upon d is our theta. Therefore, theta upon n. N is given 4 by 3. Thus, the new angular width of the bright fringes is 0.15 degree. Now here the numerical of exercise depends on the interference completed. Last is 10.7. Okay. Now in illustration, the first illustration 10.1. So that is given like that way. What speed should a galaxy move away from us so that the wavelength of the sodium light is observed 589.6 nanometer instead of 589 meter. So we have to find out the speed of a galaxy. Speed of a galaxy with respect to us. The wavelength of sodium light, wavelength of sodium light, lambda, Whittle lambda wavelength is 589 nanometer. But due to the speed of a galaxy, the observed value of wavelength is lambda dash is 589.6 nanometer. So we have to find out the speed of a galaxy moves with respect to us so that the wavelength of the sodium light is observed 589.6 nanometer instead of the 589 nanometer. So here, first, what is the difference in wavelength? Therefore, delta lambda is equal to measure value minus Whittle. Therefore, 589.6 minus 589 is equal to 0.6, which is greater than 0. Here, delta lambda is greater than 0. Therefore, wavelength is increases, but the frequency decreases. So here, lambda is increases, but frequency f decreases. Now, corresponding to such wavelength, whatever the spectral line obtained, corresponding to this, the spectral line obtained towards red end. Thus, that is the red shift. Thus, it is called red shift. It is called red shift. Thus, the galaxy is moving away so that galaxy is moving away from us. Therefore, the speed of a galaxy is V is equal to C into delta lambda upon lambda. C is the velocity of light. That is, we know that is the 3 into 10 is to 8. Delta lambda 0.6 upon lambda. Lambda is 589 nanometer. So 589 into 10 is to minus 3 meter. Clear this? Therefore, the speed of a galaxy is 3.056 into 10 is to 8 meter per second. That means the galaxy is moving away from us with the speed quite more than the speed of a light. Therefore, the wavelength increases. Therefore, in visible spectrum, the wavelength is increased towards or shifting towards the red end. So that is known as the red shift. Now, illustration number 10.3. Now, what is the separation between the two bright fringes or the two dark fringes? In Young's double-slit experiment, the wavelength used is of the green blue light of wavelength 500 nanometer. Lambda is given the 500 nanometer. The distance between the two slits D is given the 1 millimeter. 1 millimeter. So there is the 500 into 10 is to minus 9 meter. Here 10 is to minus 3 meter, and screen is placed at 1 meter distance. What is the separation between the two bright or the two dark fringes? Or what is the fringe width? Fringe width. Again, in Young's double-slit experiment, to obtain the interference fringes, the blue light or the blue-green light is used of wavelength 500 nanometer. The distance between the two slits is 1 millimeter, and the screen is placed at 1 meter distance from the slit. Find the fringe width or the distance between two bright or the two dark fringes. Therefore, the distance between two bright or dark fringes the distance between two bright or dark fringes is, there is the beta is equal to lambda capital T upon small t. Lambda is given 500 nanometer. So 500 into 10 is to minus 9 into 1 upon D, 1 millimeter. So 1 into 10 is to minus 3. Therefore 5 into 10 is to minus 4. 5 into 10 is to minus 4 meter. So there is the separation between whether there is the fringe width is the fringe width in Young's experiment. There is very easy numerical, only we have to substitute the value in equation beta is equal to lambda D upon